Okay, our next presenter is somebody who is the youngest presenter to ever give a presentation at any of our conferences. And I think 2 years ago, was it 2020, that was your first presentation? And at that time, you're about 16 or 16 years old in the 10th grade? Yes. And then he presented a couple presentations last year. Early on, through some online communication, I had put him in touch with Eric Dollard, and they had been collaborating, and Griffin is actually one of the few that I know of that not only understands a lot of the Eric Dollard material, but actually has replicated probably more of Eric Dollard's experiments than anybody I know. Griffin is a mathematician and experimenter. He focuses on the development of new electrical concepts and inventions which pertain to the field of power distribution and radio frequency engineering. Although he recently completed high school, he's a self-taught engineer who is predisposed to understanding the function of natural phenomenon through the lens of an electrical standpoint. Griffin has been very instrumental in a lot of the stuff going on at EPD Labs and with Eric. There being limited resources at EPD Labs down there, Eric does a lot of writing, and the two main projects he's kind of interested in, not kind of, but obsessively passionate about, is the electrostatic rotary converter and a lot of the telluric transmission. And Griffin, Apparatuses, and a few others kind of behind the scenes are all involved in some of these telluric experiments, which have been really successful, and it's really important because it really keeps Eric kind of going to see that things are happening and that there's people who are paying attention, listening, and actually applying what they learn. This next presentation, I think it was last year, one of Griffin's presentations was on these high-frequency illumination methods by Tesla. He showed a lot of different variations of different bulbs, and the devices that he built looked like they were right out of the late 1800s, early 1900s. He blows his own glass, makes his own bulbs, fills them with the gases, and he's one of the most incredible experimenters I've ever known. This is going to be part 2, which is going to be a follow-up to that presentation, so help me welcome Griffin Brock.
Okay, well, this presentation will commence just with a brief background and summary of what happened last year. Now, as Aaron had already stated, this presentation will just exemplify the understanding of Tesla's illumination apparatuses, and specifically his high-frequency, high-vacuum bulbs. Now, throughout this course of this presentation, I will just showcase the bulbs before the stage and just show their development and what exactly they could accomplish. So before we get into this, let's go into the background of last presentation and just last year as a follow-up. So we can see here, this is a crude, but this is one of the first bulbs constructed by myself using some very crude glass blowing methods, but nonetheless it's supposed to replicate the Tesla carbon button lamp. Now the way that this lamp works, which we could see here with an evacuation stem which is designed to pump out the various gases and ultimately obtain a high vacuum within the sphere itself. The carbon button lamp, which comprises a small carbon sphere at the top of a stem which is supported by a glass lead-in stem, and it is encased around an aluminum electrode or a sheath, which Tesla describes as being an electrostatic screen. Now this bulb, as Tesla describes, is supposed to give off incandescent light by due action of the heating carbon actual button itself right here. Now it is supplied with a terminal at the base right there, which is therefore connected to some other high-frequency alternator or high-frequency coil setup, which I have displayed here. Now Tesla does state, and what I do want to point out is that this carbon sphere, which he describes is containing a silicon carbide mixture baked in a tar resin. Now, of course, this type of resin is difficult to achieve on a practical scale, especially when a lead-in electrode comprising a material called tungsten is used. Now, because it is carbon, carbon does not adhere to tungsten that well, and of course, we have to go around this and find shortcuts. Now, mind you, this depth, which we will see, is resulting in an effective copper volume, or which I have derived as the effective secondary volume in this case. So, since this is not necessarily a typical transmission system in the conventional or academian point of view, we see that the secondary coil, I'm now taking the example of this entire setup, that the secondary coil, which is shown as the elongated coil near the bottom, that has an effective copper volume, or in essence, a certain amount of copper which is being employed. We could actually determine how much copper is being used at its operating frequency, and by that we could match the actual weight or the actual cubic volume of the copper being used and match it to that of a primary coil, which is shown as the 2 turns of copper strap at the bottom, and get a rough approximate idea of how much copper the primary should have. Because of the form material and the very winding of the apparatus, it is not able to obtain high potentials at an efficient cost. But in this case, we are simply operating the coil with, right now, I would say 30 to 35 watts of radio frequency power, and we are obtaining a spark at the very top of the terminal, which by comparison could be roughly a kilowatt. Yes. As compared to modern Tesla coils, which require many kilowatts to obtain something similar but slightly greater than that. And as he starts to increase the power and slowly adjust the frequency, we can see that the flame or the brush discharge emanating from the terminal is growing. So that just simply demonstrates the effect of high efficiency in the case as applied to a Tesla magnifying transmitter. Now moving on, we enter the realm of disruptive discharge. Now technically this is more of a continuous wave type of input, not in the case that we just showed, but more of a constant input of energy rather than a disruptive discharge unit which Tesla originally worked with. Now in the case of Tesla, we could see that as presented in his 1892 lecture, he presented a very interesting and very early Tesla coil, so to speak, which is otherwise known as a high-frequency, high-potential setup, which in this case, we have a secondary provided with an adjustable primary gap, which allows a discharge to pass. Mind you that this is a very early design of his apparatus. But although we could still see that there is a balanced condenser configuration on either side to minimize and just to distribute the disruptive transient discharges which emanate from this spark gap. Now this spark gap, he deduced, must be synchronous or therefore rotary so that to obtain the greatest efficiency. Now I have not included this in the presentation, but according to his Colorado Springs notebook and his various descriptions and diagrams, we could see that in addition to these series condensers, there's also a parallel or shunt condenser which goes across the primary. Now we will exempt the overall construction of the primary and secondary in regards to his Colorado Springs setup, but nevertheless the tank circuit remains similar. Going back to that, we would have a shunt condenser which minimizes the current consumption generated by the spark gap, but then also the current consumption of the primary coil, which effectively smooths out the discharge. And of course, he later adds a variable inductance coil so that to effectively tune the primary and disruptive discharge tank circuits to that of the secondary and extra coil. But that, of course, is for that explanation for a different day. And this is a close-up of Tesla's alternator, which in respect, going back to the Alexanderson alternator patents, is similar in that sense, where you have many pole projections here, which are wind in series. Now we could see that unlike a normal generator or alternator in any sense, where we would only have 6, 12, or 32 projections, we could see that they are quite close in proximity, and that the armature is almost an identical image of it. Now this armature, which is shown here, is provided with a very hair-fine gap, which is then spun at rapid alternation, which is, of course, even at that time, quite tricky to engineer. But nevertheless, you would be able to obtain high-tension, high-frequency currents, which were perfect for these type of operations. Now, this is Tesla depicted in the late 1910s, shown with his high-frequency alternator. This is one of the only known pictures of this actual alternator, but it is quite small in comparison and resembles a very simplistic disc, although the simplicity soon goes away when the actual pole projections and the winding is shown. Now we can see that this is a photo of one of Tesla's original devices, and this is actually a commercial grade induction coil or high frequency induction coil, similar in design to this one, which was illustrated and marketed in the early 1900s by the IE Knot apparatus company. Now this photo was taken by Tesla, in which he's operating this device in a single wire X-ray configuration, which he has a single wire bulb shown right here, just shown off the screen. Now this mustn't be confused with all the other apparatuses here, as this is most likely an electrolytic interrupter, which was common for some of the early induction coil and high tension apparatuses. But nonetheless, we could see that it still retains the same rotary spark gap here, the two high tension output points, and the encased transformer shown within the box there. Now, if we take a look at these strong lines, we also have one on the 520 nanometer range right here. And if we consult our chart, we can see, where is it? It's hiding from me. There we go. Now, we just have to, move the decimal place once over, but we do have a strong line, and this effectively shows our intensity of the lamp, and then we also have one as well on here, but then the other ones do not appear. So that means if the lines are appearing and it's not silicon, then that means it's something else also interacting with these superheated silicon atoms. Now, if we were to take a look at oxygen, this is where it gets interesting, because then we are actually able to see that there are very similar field lines, strong lines, which present themselves in the atomic emission spectrum. And of course, if we place them on top of each other, we could see that the two strong green lines seem to match up with oxygen, but also that of silicon. And here, in the 600 nanometer range, and then approaching the 700 nanometer range, we could see that we also get the mixture of silicon and oxygen. The color associated with the actual bulb is associated with silicon and oxygen. Now this does show itself. Now this presents itself in all various high vacuum devices, such as the brush bulb, and very simple bulbs such as this. But what is rather interesting is that when you start incorporating various vapors, such as mercury and caustic potash, which is similar and what would be ultimately found in the Sprengel pump, which Tesla would have used in the 1890s, then you get very peculiar effects, which hopefully maybe we could get demonstrated here. If I place this combination bulb in between the coil set, like so, and let's see if we could illuminate it. There we go. Now this is a mercury mixture, which is quite sensitive, but also with a mixture of caustic potash. Now, of course, mercury is supposed to mainly display a blue color, but as you will see, that is not true, especially when it's mixed with other superheated vapors and materials. Okay, well, let's see if we could increase the power. As we could see that the mercury vapor, along with the various other vapors, is showing its natural blue state. But if we start to slowly increase the power, okay, we're adjusting the tuning. Yeah, we can see that there's a unusual sphere separation occurring between them. But of course, as this is operating in a cosmic induction mode manner, be just a tad bit higher.
And we'll be around to do some more demos,
yes.
And so feel free to come up and check it out. So thank you very much, Griffin, everybody.